Probability is my absolute favorite subject. Unfortunately, it's seldom taught in class, so most students go through their whole math career without ever learning probability. For that reason, I decided that I should go over probability fundamentals before tackling every formula and theorem that you need to know. Probability is the rate at which something occurs. The most fundamental concept is that the probability of an event is the number of valid combinations over the number of total combinations. Let's look at an easy example. What is the probability of rolling a 2 on a die? The number of valid combinations is 1, because there is only one way to roll a 2. The number of total combinations is 6, because there are 6 different ways that you can roll a die. Hence, the probability of rolling a 2 is 1 over 6. If A represents the event that you roll a 2, then P of A is 1 over 6. The next concept is that OR means add. If you're asked to find the probability of one event or another, you find the probabilities of each and you add them up. Let's take our first example and slightly change it. What is the probability of rolling a 2 or a 3? We know that the probability of rolling a 2 is 1/6 and the probability of rolling a 3 is 1/6. If we use the union symbol to represent the word OR, we get that the probability of A or B is 1 over 6 plus 1 over 6, which is 2 over 6. That is 1/3. Again, this is because OR means add, and we're looking for A or B. The third principle is that AND means multiply. Let's look at the same example. However, we're going to be rolling the die twice. We want to get a 2 first, and then a 3 second. Using the intersection symbol to represent AND, we get that the probability of A and B is 1 over 6 times 1 over 6, which is 1 over 36. If we look at all possible combinations, we see that there are 6 rows of 6, so there are 36 total combinations. 2, 3 only appears once, so the probability of getting a 2 and then a 3 is 1 over 36. So far, we have been looking at independent events. That means that A and B don't affect each other. Let's change up our question so that A and B are dependent. Now we're rolling 2 dice. What is the probability of rolling a 2 and a 3? This is equal to the probability of the first one being 2 and the second one being 3, or A being 3 and B being 2. This is dependent because your second roll relies on your first. If your first roll is a 2, your second must be a 3. If your first is a 3, your second must be a 2. It changes based off of the first roll. Now thankfully, we can break this up into independent events. Let's use the intersection union notation. The probability of A equaling 2 and B equaling 3 is 1 over 6 times 1 over 6. If A is 3 and B is 2, it's also 1 over 6 times 1 over 6. And because it's the first case or the second, we add the 2 together. That gives us 1 over 36 plus 1 over 36, which is 2 over 36 and 1 over 18. If we look back at the chart, we can see that there is one pair that is 3, 2. So there are 2 ways that we can roll a 2 and a 3. Let's now look at the concept of replacement. Imagine we have a deck of cards. I want to find the probability of drawing a king of hearts, placing it back in the deck, and then pulling out the queen of spades. There are 52 cards and only 1 king of hearts and 1 queen of spades. The word "and then" suggests that we multiply the 2 together. We get 1 over 52 times 1 over 52, which is 1 over 2,704. This time, we're going to find the probability of drawing a king and a queen simultaneously. Whenever 2 events are happening simultaneously, act like they're happening in immediate succession. In other words, one happens and the other happens right after. In this case, we want to get the king or the queen on our first draw, and then get the other one on our second draw. The trick here is that we're not replacing the card. Replacing the card is when you put it back in the deck like the last example. But if they're drawn simultaneously, the first card is obviously not being replaced. This causes the second draw to have a different probability. The first draw is 2 over 52, since there are 52 cards and I'm looking to pick up 2, either the king of hearts or the queen of spades. On my next draw, I only have 1 card remaining that I want to choose, whichever card I didn't pick on the first try. Since we pulled 1 card out of the deck, there are now 51 cards left, not 52. So choosing the remaining king or queen has a probability of 1 over 51. This equals 1 over 1,326. We're now going to look at what I like to call pool problems. We're going to start with a box, and this box represents all events, so there is a 100% chance that you'll land inside the box. I'm now going to draw a blue pool inside of the box. This represents all possible ways of achieving event A. The next pool is pink and represents all the ways that you can achieve event B. Then the intersection of the two pools is the set of events that satisfy A and B. One formula we can derive from this is that the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. A or B represents all the space covered by pool A and pool B. The problem is, if we add together the two pools, the crossover section is added twice. That is why we have to subtract it once. For our example, let's look at the probability of drawing either a black card or a queen. We can apply our formula. We know that half of our cards are black, so we have 26 black cards. We have 4 queens, and we have 2 black queens. This means that the probability of drawing a black card or a queen is 7 over 13. Lastly, I want to look at another application of the pool problem. Let's look at the probability of event A given that B is satisfied. P of A given B is notated with a vertical line as shown. If we're given B, we know that we're somewhere inside of pool B. That makes probability of B the denominator. All possible combinations are in pool B. For the numerator, we want to satisfy event A. But if we're bound by pool B, the only place where event A is also satisfied is the section where the pools overlap. So our numerator, our number of valid combinations, is P of A and B. Let's find the probability of choosing a queen given that the card is a spade. Using the formula, we know that P of Q given S is the probability of Q and S over the probability of S. The only card that satisfies Q and S is the queen of spades. So the probability of Q and S is 1 over 52. The probability of choosing a spade is 13 over 52, since there are 13 spade cards in the deck. If we look at the full deck, we see that there are 13 spades, and only one of those is a queen, so the probability, again, is 1 over 13. Now that's all for now. I'm finishing up my geometry video for the series of every formula and theorem you need to know for Math Team. Sometime after that, I'll be releasing a probability video that takes these basic concepts and applies them to more complex formulas and more difficult problems that you may see on a Math Team test.